We've seen that an integral can be improper if it has infinity in one of its bounds, but that's actually not the only way for an integral to be improper. So let's take this integral as an example, the integral from 0 to 1 of 1 over the square root of x. If you think about the fundamental theorem of calculus, right, it helps us calculate definite integrals, but it has some preconditions. An integral from a to b of some function f of x, in order to use the fundamental theorem of calculus, f has to be continuous on the interval from a to b, and a and b have to be finite. Right? So we saw what happens if one of a or b isn't finite, but what if f isn't continuous on the interval? In fact, that's exactly what's happening here. This function 1 over the square root of x, from 0 to 1, it looks something like this. It has this, as x goes to 0 from the right, this function actually goes up to plus infinity. So this time, it's sort of as if rather than having an infinity in our bounds, we have an infinity in the integrand, is kind of what's happening. But, you know, just like when we had an infinity in the bounds, we can handle this by sort of doing a little surgery on the interval that we're integrating over. Instead of integrating all the way down to 0, we can just integrate down to some value t, and t will be a little bit bigger than 0. So integrate 1 over the square root of x. Now for this integral, there's no problem. We can use the fundamental theorem of calculus. But then when we're done, we'll take a limit as t goes to 0. But actually, right, we want to avoid everything to the left of 0. So we need t to go to 0 from the right. So to indicate that, remember, we put a little plus superscript on our 0 here. So we can calculate this integral, the definite integral, in the usual way, and then just take a limit as t goes to 0 from the right. So I should say that we're taking a limit from the right because the t is our bottom bound. If we had to do surgery to avoid one of these infinities at a top bound, then this limit would be from the left instead of from the right. Okay, anyway, now that we have done our surgery and sort of cut away the discontinuity, the infinite discontinuity of our function f, we can go ahead and calculate this the usual way. So limit as t goes to 0 from the right. Antiderivative of 1 over square root of x is, let's see, I think it's going to be 2 times the square root of x. And we need to evaluate it from t to 1. So this is limit as t goes to 0 from the right of 2 times, so the square root of 1, which is 1, minus the square root of t. Okay, and now we can evaluate the limit. Notice that it's a good thing that the limit is one-sided here, because the limit of the square root of t as t goes to 0 from the right is 0. But the two-sided limit as t approaches 0 of the square root of t doesn't exist. So it would be a mistake to not have a one-sided limit here. We would get something undefined when in fact it should just be 0. So what we get is 2. Up on our sketch, this infinitely long spike going up all the way up to x equals 1. This is exactly 2 units of area, it turns out. So in general, what's happening here is if our function isn't continuous at some point in the interval where you're integrating, you have to cut away that point of discontinuity by, so we're integrating from a to b. If our function is discontinuous at c, we have to cut away that discontinuity by first integrating from a up to some value t, and then take the limit as t goes to c from the left, that's That's this part. And then we have to do another integral. We take the integral from t up to b, but this time we let t go to c from the right. That's this part. Of course, if the discontinuity is at one of your initial bounds, then you get only one of these two pieces. Just like with improper integrals that come from an infinity in the bounds rather than in the integrand, in this situation, we call, if these limits exist, then we say that the integral converges, and if one of them doesn't exist, or if either of them is infinity or minus infinity, we say that the integral diverges. One thing that's important to notice here is if you do these integrals and you get, say, infinity for one of them and minus infinity for the other, it's not okay to say that this is 0, because infinity minus infinity actually isn't defined. What infinity minus infinity should mean sort of depends on context, and in many contexts, including most of these contexts where you have an improper integral like this, there's no sensible way to define what this infinity minus infinity should be. So don't be tempted to just say, oh, well, this is the same thing minus itself, so it's 0. No, infinity doesn't work that way. Let's look at one more example. Let's find the integral from 0 to 2 of 1 over x cubed. So the thing about this sort of infinite discontinuity in the integrand is it's easy to miss. Right, just looking at this, you wouldn't necessarily notice that this is an improper integral, but because 1 over x cubed is discontinuous at the bound 0, this is an improper integral. So we have to do our little limit surgery to cut away that discontinuity. So limit as t goes to 0. Since this is a bottom bound, again, we have to take the limit as t approaches 0 from the right. We're going from 0 up to 2. And so we have to start at 2 and go down to some value t, and then let t go to 0 from the right. Integral from t to 2 of 1 over x cubed dx. And now we're free to evaluate this integral using the fundamental theorem of calculus. So limit as t goes to 0 from the right of, let's see, I guess it's going to be minus 1/2 1 over x squared from t to 2. So limit as t goes to 0 from the right of minus 1/2 times 1 over 2 squared minus 1 over t squared. And now when we take a limit as t goes to 0, this 1 over t squared part is going to infinity. And so this limit is plus infinity, and so this integral is divergent. Okay, so because there's no sort of obvious indicator that this is an improper integral, we now sort of every time we look at an integral, we have to pause and ask ourselves, hey, wait, is this function continuous everywhere on the interval from 0 to 2, including 0 and 2? So now we have to do this for every integral we ever look at, because there might be an improper integral hiding.